Thank you for introduction. I'm Yosuke Oyama, a PhD student at Satoshi Matsuoka Lab in Tokyo Institute of Technology. I'm currently a student at Tokyo Tech, but 3 years ago, when I was a master student, I visited ETH Zurich for 2 months using its summer research student fellowship program. And I wrote this paper with Tao, accelerating deep learning frameworks with microbatches, and presented at Cluster 2018. So today I will talk about this topic. By the way, in this presentation, I used the latest software at that time, cuDNN 7, but we now have cuDNN 8 and A100 GPU is being available. So I only show results of cuDNN 7 on V100. So this presentation is about the computational performance of convolution. Convolution is a key operation in convolutional neural networks, one of the most commonly used types of deep neural networks. The left figure shows 2D convolution, which we usually see in many deep learning textbooks. And the right one is its pseudocode. It is 7 nested for loops for 2D convolution, including a mini-batch loop and 2 channels loop and 2 spatial loops and 2 kernel or filter loops. So it's too heavy computation. And as many HPC applications use BLAS libraries for its linear algebra computations, the cuDNN deep learning kernel library is the de facto standard library to compute deep neural networks, especially for convolutional areas, if you run your deep learning application on NVIDIA GPUs. Interesting point of cuDNN is that it provides a wide variety of convolution algorithms, including gen-based convolution, where the input tensor X is transformed by using a function called m-cuCall, so that the following gem between the weight matrix becomes equivalent to convolution. And another one is Winograd algorithm, which perform convolution as element-wise product in the Winograd train. Please refer to the paper if you want to know why it works. And FFT-based convolution, which is somewhat similar to Winograd, but convolution is done in the frequency domain. Their all algorithms are equivalent, and the library provides a simplified interface. So what you have to do to use either of the algorithms is just to specify algorithm ID and provide sufficient backspace to the library, which is a piece of GPU memory used to store intermediate data, shown in light blue color in this figure. So you may think that we just need to call cuDNN with the fastest convolution algorithm, which is true, but the problem is the workspace is too huge. So this plot shows memory consumption in bars and computation time in lines of AlexNet, old-fashioned network. I use 3 different workspace sizes in this figure, 8 megabyte and 64 megabyte and 500 megabyte. But you see the workspace shown in blue is as large as memory footprint to store the network itself, shown in red and green. So this figure says we get like 1.5 times of speedup by using twice GPU memory size. But this doesn't make sense because in deep learning frameworks, we typically use almost all GPU memory by using a large batch size to maximize the computational efficiency. So there is a trade-off between efficiency and the choice of convolution algorithms. So we found a solution to mitigate this large workspace and to use faster convolution algorithms with limited amount of workspace. So this is to the convolution, and you can see that the last line 8, multiply and add line does not have dependency between itself on different n, which is the iterator of the outermost loop. But the workspace size is required by cuDNN is determined by layers configurations, including the mini-batch size n. So we just split the outermost loop. In other words, we call cuDNN 2 times or more for each layer. So the summary of this talk is in this slide. We propose a library called MicroQDNN, which is a wrapper library for cuDNN, which performs runtime auto-tuning to split a mini-batch into what we call microbatches by applying loop splitting. We propose several methods to do the auto-tuning part using dynamic programming and integer linear programming, and we also provide an interface for further performance analysis and perhaps for high-level optimization. This middle figure shows how MicroQDNN works. For example, it performs 2 convolution calls to cuDNN for conv1, and actually it faster than calling once because it saves workspace requirements to use faster convolution algorithms like FFT-based convolution. And as contribution, we achieve considerable speedup against cuDNN itself on V100 GPU and so on. So then I briefly explain MicroQDNN's algorithm. As I explained, almost all deep learning frameworks rely on cuDNN, which runs on NVIDIA GPUs. And frameworks themselves are usually written in C++, and researchers usually use Python to describe their own models on the top of the framework. So we create MicroQDNN as a C++ wrapper and insert it between a framework and cuDNN. So MicroQDNN overrides some cuDNN functions like convolution operations to perform auto-tuning, which is shown as number 1 in this figure. Another side effect of adding MicroQDNN between the framework and cuDNN is that it can capture each call to cuDNN and correct performance metrics by running cuDNN internally. So in this paper, we demonstrate that this can be used for further performance analysis by using external interface as shown in number 2. This function resembles to cuDNN's logging function, which is enabled by setting cuDNN log info environment variable, but it only logs, it only records calls and corresponding augments to cuDNN for debugging purpose. So this is the difference. And then I explain how MicroQDNN is implemented. So when a deep learning framework compute a convolutional neural network, it first gets the fastest algorithm for each layer by calling cuDNN get convolution forward or backward filter and backward data algorithm function, and then allocate workspace, and then call cuDNN convolution functions in the training loop. So we define a MicroQDN handle class, and when cuDNN handle in the framework is replaced with MicroQDN handle, the framework calls overloaded functions to run optimization in MicroQDN library. So yeah, the framework transparently calls MicroQDN without knowing its algorithm, and MicroQDN calls cuDNN inside of it. And for optimization, we propose two different ways to split the convolution loop, and users can select either of them. Workspace reuse, one of them, is a simpler one, which just apply dynamic programming to compute the optimal combination of microbatch sizes. I explain later. Workspace division is a more complex one, which is used in the case where a unified workspace is shared by multiple convolutional layers. Both has pros and cons, but the problem of workspace reuse is that it may cause memory overflow in some frameworks because the total workspace size can be order of the number of layers. But workspace division is safe because the total workspace size is controllable. So I explain workspace reuse first and then workspace division. So workspace reuse is easy to understand problem. So the problem is given a batch size B, gets the time to compute this batch B by calling one cuDNN convolution T micro B, or split the batch into two or more batches. So for example, T60 might be T micro 60, which is a computation time of cuDNN to compute a convolutional layer with a batch size of 60. But T120 might be the sum of two cuDNN calls. So by repeating this step, we compute the computation time of the mini batch itself. So this is the pseudocode of this algorithm, and the output of this algorithm is called what we call configuration, which is a list of algorithm IDs and their microbatch sizes. For example, if the output is this means that MicroQDN will perform FFT-based convolution for the first two microbatches size of 100 and use gen-based convolution for the rest of the samples. And we found some tricks to be combined with workspace reuse algorithm to improve the tuning performance. First, the selection of microbatch sizes can be limited to power of 2 to reduce the overhead of MicroQDNN without losing its performance. This is because we have to actually run QDNN to correct this T micro computation time of each QDNN call. So limiting the choices to power of 2 microbatch sizes drastically reduce the overhead. So I define 3 different microbatch size policies: all and power of 2 and undivided. Undivided is only used for debugging purpose, and I will show how is the difference between them later. Another trick is to use pseudo-half configuration. This is more engineering trick, but in cuDNN 7, half precision is already available, but some algorithms like FFT-based conversion is available only on single precision float. But cuDNN kindly provides a knob to use such algorithms for half precision data transparently by using this pseudo-half data type. So we include both true half and pseudo half into our selection of available convolution algorithms if half precision data type is used, assuming that these algorithms might be faster than true half convolution algorithms. By the way, we don't use true half algorithms if users use single precision float because it loses precision. Okay, then I'll explain workspace division. I think I should show a figure first because there is a lot of math here. So the problem is if we have a fixed size of workspace, which is the case in many deep learning frameworks, how much we can combine different microbatches and different algorithms. And this figure shows answer in convolutional layer, the second convolutional layer of AlexNet. In this figure, all of the available choices are shown by using the workspace division algorithm, each of which shows the time and required workspace size as a point and the breakdown of workspace as a bar. So for example, the left top point shows that 2 convolution kernels are performed using FFT tiling algorithm. So as we increase the workspace size, more efficient algorithms can be used, even several algorithms are combined. On the other hand, if microQDN is not used, the fastest algorithm is implicit precomp-gem, the yellow one, because other algorithms like FFT or Winograd originally require much more workspace, like 200 megabyte. So this problem is formulated as ILP, integer linear programming program, because the constraint is workspace size, which is integer, and the objective is to minimize the total computation time. So this algorithm outputs a configuration, a list of microbatches, and its convolution algorithms, just like workspace reuse. And I explain here that microQDN microQDN caches every QDN performance metrics like time and required workspace size for each layer into a file-based database, as shown here. So this information can be used after running benchmark on the framework. So in this paper, we explain that we can actually use this information to do multi-node heterogeneous cluster data parallel training, which is a bit tricky, but without modifying the framework itself. But I think I have to skip the details because I would be running out of time. But anyway, we emphasize that microQDN can be used to collect performance information without modifying the framework itself. So we evaluate our library by using 3 different generations of GPUs and 2 frameworks, Caffe and TensorFlow, and various networks and the DeepBench benchmark. First of all, this experiment illustrates how microQDN work. So in this figure, it shows computation time as bars and microbatch sizes as labels in bars of the second convolutional layer of AlexNet on P100 GPU. And here I use 3 different microbatch splitting policies I explained before: undivided and power 2 and all. And undivided is equivalent to cuDNN, but because this does not divide the minibatch size. Here we can see that all algorithms can split the minibatch size of 256 into group of 32 samples and 48 samples, and it uses FFT tiling and Vinograd algorithm to achieve more than 2 times of speedup with the same workspace constraint. And we also see that even though microbatch sizes are limited to power of 2, we can get about 2 times of speedup as shown in the second row of this plot. Here, without microQDNN, cuDNN has to use gen-based convolution because FFT-based convolution requires more than 200 megabytes of workspace. Then I evaluate the performance of MicroQDNN is DeepBench. DeepBench is a benchmark including various types and various shapes of different layer types appeared in deep neural networks, and it includes about 100 convolutional layers. Here I show relative speedups of DeepBench's convolutional layer against cuDNN on 3 different GPU generations from Kepler to Volta, and with different configuration. I mean, single precision float and half precision with tensor cores. Here, MicroQDNN achieves about 1.6 times on average on the latest GPU at that time, V100 GPU, even if tensor cores are used. Interesting point here is MicroQDNN uses pseudo half in about 70% of the layers, which implies that the single precision float algorithms are still useful for some cases if workspace size if the workspace size is efficiently divided. And MicroQDNN also achieves like 1.2 or 1.7 times of average speedup for 3x3 kernels on P100 and V100 respectively, which is one of the most commonly frequently used filter size for convolutional layers. So we then combine MicroQDNN with the deep learning framework Caffe and evaluate the speedup with AlexNet on 3 different GPUs with 3 different workspace sizes. Here, in all of the GPUs, we achieve like 1.4 to 1.8 times of speedup when the workspace size is 64 megabytes. By the way, 64 megabytes is the default workspace size used in Caffe 2 and Chainer framework, and Caffe uses 8 megabytes by default. Another important observation here is MicroQDNN achieves less speedups with 2 tiny workspace size, I mean 8 megabyte, or huge workspace, 500 megabyte. This is because if the workspace size is too small, like 8 megabyte, MicroQDNN cannot utilize it, even though it split the mini batch into microbatches. And if huge workspace is available, cuDNN can just use efficient convolution algorithms like FFT or Vinograd without dividing the mini batch. So in that case, we don't have to use MicroQDNN. But again, we want to emphasize that in many cases, the GPU memory for deep learning, the GPU memory becomes almost full for many deep learning applications because researchers want to maximize the mini batch size to get better computational efficiency. So yeah, we believe MicroQDN can bring better performance for practical cases. With Workspace Division policy, we get small speed up on ResNet 50, but this speed up cannot be achieved by Workspace reuse on Caffe because in Caffe each layer tries to allocate at most 64 megabytes of workspace, for example, which result in out of memory error. But with Workspace Division, the total workspace size is specified by the user, and the total workspace size does not exceed that limit. So we can accelerate convolutional layers without out of memory errors. This figure shows the visualization of assigned total workspace for AlexNet with workspace reuse and workspace division. We set the same total workspace limit, but workspace division allocate more workspace for COM2 and COM3, implying that MicroQDN can spare more memory for time-consuming layers by using its IIB optimizer. This is last experiment, a case study of heterogeneous cluster optimization. Here we assume that we have 3 available GPUs, 3 different available GPUs, and want to train ResNet with data parallelism by setting different local batch sizes for each to minimize the barrier overhead among the GPUs. So here we show that by collecting computational time of each layer of each GPU by MicroQDN via the file-based dataset, file-based database, we can analyze the performance independently from the framework type. So this slide is the last slide, and I here show takeaways of my presentation. First, MicroQDN is a freelance library. It doesn't change what you do on your framework, but it is guaranteed that it may bring better performance, but do not slow down your training jobs, and is theoretically applicable to almost all frameworks if the framework works on NVIDIA GPUs. And source code is available here, and the conference paper and the archive version are also available online. So this is the end of my presentation.